Hello everyone. My name is Emil Biju and I'm from IIT Madras. Today I'd like to present my work on vocabulary constrained question generation with rare word masking and dual attention. Now, question generation is the task of generating questions from a text passage such that the answer to the question can be derived from information that's available in the passage. There's been a lot of work that has come up in this area for quite some time, starting with rule-based approaches like semantic role labeling, syntactic parsing, and part-of-speech tagging, which leverage the inherent structure of the statement to generate the question. Later on, there was work on GRU and LSTM-based neural encoder-decoder frameworks that first encodes an input sentence and then decodes a question from it. Besides, there has also been work on more sophisticated transformer and BERT-based approaches for question generation. Now, the applications of question generation are quite varied. One could think of automated tutoring and interviewing systems, or chatbots and virtual assistants, in which a system could be made more interactive by enabling it to ask questions and probe the user. Let me talk a bit about my motivation behind this work and how I have tried to improve upon existing work in this area. Much of the existing work in this area makes use of a large, predefined vocabulary to train the neural encoder-decoder framework. There are two key disadvantages that I observed with this method. Firstly, a large vocabulary means greater training and inference times, greater memory usage, and a larger number of network parameters. This in turn increases the computational requirements of the model and for both training and testing the model, in fact. A predefined vocabulary, on the other hand, may not include context-specific words from the input sentence that would make our question more specific, meaningful, and accurate. Now, I refer to an interesting work performed by Schonel and a few others way back in 1956, which stated that around 74 to 94% of conversations and written text in English are covered simply by the 1,000 most common words. Now, I'd like to ask a very pertinent question. How would a human learner construct a question? Let us consider this sentence as an example. Apollo 11 was the space flight that first landed humans on the moon. Now, I would say that the first step in constructing a question for this statement is to identify a keyword from this given statement. In this case, I choose Apollo 11 as the keyword. The next step would be to choose an interrogative word like when, what, how, why, etc. In this case, we choose what because we are questioning the name of the particular space flight. Once this is done, we begin to mentally guess or preempt the outline or the skeletal structure of the question. In this stage, we may want to think of common words or an appropriate placement of the interrogative word, the prepositions, articles, and conjunctions in order to generate a basic skeletal structure. Further, we would leave blanks in those areas which we would want to fill with more specific words later on. Given that we have a skeletal structure, we now observe certain keywords from the input statement like space flight and moon, which are more specific and which are words we cannot possibly expect to find in a short or small vocabulary. And the next step would be to identify those keywords, those very specific keywords, and then place them at appropriate gaps in the skeletal structure that we've already created. Now, there are a few key learnings from this exercise. First of all, the first three steps involved here only require us to predict words from a small-sized vocabulary, whereas the last two steps would require specific words that have to be pointed to from the input passage that we have. And that brings me to my proposed architecture, which consists of two discrete modules, one for performing each of these tasks. They are namely the question structuring module and the word pointer module. The word pointer module generates the question structuring module would generate the skeletal structure of the question using common words from a small sized vocabulary. The second is the word pointer module, and this one would point out rare words from the input passage to fill the gaps in the skeletal structure that has already been created. For this work, I've made use of the Stanford question answering dataset, which gives us a huge corpus of question answer pairs created by crowdsourcing. I define our vocabulary as the set of 1,000 most common words from this dataset. Now I'd like to formally define what my question structuring module architecture looks like. This module makes use of an encoder-decoder framework whose input is the sequence of Elmo embeddings of each input sentence. This sequence is passed through a bidirectional LSTM layer to generate a sequence of encoded vectors. The decoder consists of a unidirectional LSTM layer, which also uses a Badanou attention in order to obtain a context vector along with the previous state, and then it would predict one of the 1,000 words in our vocabulary, or a blank tag, which means it has to be replaced with a more specific word, which is to be derived from the word pointer module. Now, moving to the word pointer module, we would like to ask another pertinent question. Can we make use of the attention scores that were obtained from the question structuring module in order to identify the word from the input sentence which would be most relevant to replace each blank tag? Now, I observed while this does partially work, one of the challenges is that training a separate network would yield better results, and therefore I've chosen to do the same. The next question we would like to ask is whether we can make use of the hidden states of the decoders from the question structuring module at each stage where a blank tag was earlier predicted. Now, this appeared to work quite well for me, particularly because the hidden state carries contextual information regarding the intended word for that time step. It is also the same hidden state that conveyed to the decoder that the expression of this information would require a rare or uncommon word, and that a blank tag must be predicted at this stage. Moving to the specific architecture of the word pointer module, what we have here is the question structuring module that we have seen already. And we define two sequences, Q1 to Qi and K1 to Kj from the outputs of the question structuring module. Now, K1 to Kj is simply the sequence of encoded vectors corresponding to rare words in the input sequence that did not figure in our 1,000-word vocabulary. Whereas Q1 to Qi is the sequence of hidden vectors that correspond to the time steps when the decoder earlier predicted the blank tag. These vectors are passed to a bidirectional LSTM layer to generate a new set of encodings. We use an attention framework to find which vector from the Kj sequence is closest to each vector from the Qi sequence. Each of the Qis is assigned the word corresponding to which the attention score is the highest. The word would replace, this particular word which is chosen would replace the blank tag at that location. Now, this entire module is trained in an end-to-end manner, which ensures that the encodings obtained from the LSTM are useful in assigning the highest attention scores to the right word. Now, let's quickly run through an example to understand how this architecture works in practice. Consider a simple statement: Columbus discovered America in 1492. Now, this statement contains some common words like discovered and in, and it also contains some uncommon words like Columbus, America, and the date 1492. The task of the question structuring module is to simply generate a skeletal structure for the question. It could leave blanks in those areas where a more specific word has to be predicted. Finally, the word pointer module would come in and then replace those blanks with more appropriate words that are pointed to from the input sequence. Finally, we get our resulting question: when did Columbus discover America? Now, moving to the analysis part, I conducted a short study to understand how well this framework performs in relation to a conventional LSTM encoder-decoder framework with attention. I observed that when this encoder-decoder framework uses the same vocabulary as our model in fact gives an 8.8% higher BLEU score. And when this model uses a 10,000 word vocabulary, that is when the framework is provided with a 10,000 word vocabulary, the performance of our model is on par with the performance of this framework. Now, this clearly shows that with just 1/10 the vocabulary size and with corresponding gains in memory usage, computational requirements, and training times, the performance of our model is comparable. To conclude, I wish to say that this idea can be used for several similar tasks, including translation, caption generation, and summarization. Such an approach would allow resource-constrained neural networks to be trained in a fast and efficient manner. With that, I'd like to conclude my talk. Thank you all for your patient listening, and I'd be happy to take any questions.